Hey, welcome back. So in today's video, we're gonna make another program with LabView and we're gonna practice different functions in LabView. It's basically some new functions that I'm gonna talk about, especially a for loop and a shift register. I'm gonna talk about them when we get there. But it's mostly like practicing what we have done previously. I know from the last videos with LabView, we have built the tank problem. And in the tank problem, I had given you so many information at once. So I decided to solve another problem and this time practice a little bit more. So for this specific problem, you're not gonna learn a lot like the previous video, but you're gonna practice more. The more we practice, the better we will learn. So now let's get started. So the new question is this: how can we convert, basically make a program that converts a decimal number to a binary number, and have it run? And basically, when, for example, we change 10 to a binary number with the base on the base of 2, which is either 0 or 1, we will have some lights or LED lights that are going to be turned on when the digit is 1 and be off when the digit is basically 0. So I have built this problem before. I am actually gonna run it for you now so you could see what I mean, and we will program it together here. Actually, I'm not going to show you this part because this part in here is where I've made the program the same but with the for loop, but here there's no for loop, so it's a little bit easier to demonstrate things. So let's get started. So say that we have a number 12 and we want to see what this number 12 in decimal format is in the binary format, and we want to have like 8 slots so that we can go up to, I guess, 255. So let's run this. So 12 is basically 0 0 0 0 1 1 0 0, and wherever we have 0, the LED lights are off, and when we have 1 they are on, and when we are 0 again they are 0. So for example, 200 is this number in binary format. I'll keep increasing this so to the point that all these lights are 1, and that's where if we go one more number higher, we need another slot here to fill that, right? So I'll just keep doing that, and I'm gonna show you like how it's changing. So 250, 255, yeah, 255 in binary format is all 1. So if I want to type 256, I can run it, but it's not going to give me the right results because there will be it does need another slot here. So any number, I guess, from 1 to 255, this program can change the decimal number to the binary number, and we can make it as much as we can, as big as we want, depending like what range you want to read. But I have also actually wrote this program in another way with a for loop, and this way it will also give us the same results, like 11, 15. It's still giving us the same results. Like if I make this larger and have both of them 15, they are both producing the same results. So let's build this. So this one doesn't have a for loop, so I've programmed it one by one, but this one has a for loop, so it's the program is way smaller, and it takes us it takes a smaller space in your program, but this one, it's a larger program. So now let's get started. I'll take this over here and we can start programming this. Oh, before that, let me show you how we can change a decimal number to a binary number, because I think it's going to be useful. Yeah, here. So changing a decimal number to a binary number, I'm sure you already know that, but just to refresh your mind on how we do it. This is how I've learned it at school. So assume that you want to change number, you want to convert number 12 to a binary number. So the decimal number of 12 to a binary number. So first you have to divide 12 to 2. And because it's a binary number on the base of 2, we will divide it to 2. And then you'll take the quotient of it and the remainder. And then you divide the quotient again to 2 and keep the remainder. And again, 3, the quotient part of this to 2, and then again keep the remainder, and so on until you get a remainder that is smaller than 2. That means that you can now no longer divide the number to 2. And so 12, the decimal number of 12 in the binary format of the base 2 is actually 1100, 1100. It takes only 4 slots. But if you want to have it in terms of the 8 slots, you could keep dividing 0 to 2, and if you do that, you'll get the remainder of 0 and 0, 0, because 0 divided by 2 has a quotient of 0, and 0 and the remainder of 0. So then you can add 0 on the before on the back of that one. So you'll have 0, 0, 0, 1, 1, 0, 0, something like that. So you can keep dividing this 0 to 2 to get this the number of slots that you want. For example, in this case is 8. And because all the remainders after that, after this part, all the remainder is going to be 0. So you'll have 4 zeros here and then 1, 1, 0, 0. So this is how we change a decimal number to a binary number in the base of 2, of course. So let's get started. So what is the first thing we need to do programming this problem? I'm going to give you several seconds to think. The very first thing that you need to do. Yes, is to make a control for the user, so that user can type in the decimal number that they have and then let the program change it to a binary. So the very first thing you need to do is to make a control. So that's why you come to the front panel, right click, go to numeric, and choose a numeric control. And you can type here, this is my decimal number. And you can type here that this number should be smaller than 256. So something like that. So we have built a control in the front panel. The same control will be on the block diagram too, so you can start programming on this control. So because this is a control, that means that it will send signals out. It is an input and we can change things based on the input. If it was an indicator, that means that it is an output and it can only receive signals and show it to the user. So this is a control. With a control, you can change things. It has a name on it. We can change things. And what is the thing that we want to change? Yes, we want to divide this number to 2. So now let's get started. If you divide this number to 2 using a simple divide function, so you'll divide x, which is the control number, to a 2 as a constant value, and you want to create an indicator so a user can see the results of this division. So for example, 13 divided by 2. It will print 6.5. 6.5 is not an integer. You want a number, you want a quotient as an integer, and then you want a remainder to get a binary number. So this function is not useful as long as you go and find another function in the numeric palette that does round the number towards the bottom value, something like that. So you'll round the quotient, so you'll round 6.5 to the bottom value of 6, and then get the remainder with some other functions and analysis. You can do that, it's acceptable, but there are also some functions that LabView already has, and they are built in, that makes your life way easier and your program way cleaner. So that specific function here, if you go to numeric, is the quotient and remainder. So let me click on help and open the help for you. So x divided by y, it will get the floor value of the x divided by y as the quotient, and the floor value is actually rounded to the bottom value. And then the remainder will be x minus y multiplied to the quotient. Simple math, you all know this. So you can use this function and clear whatever we have done here and just have it way easier. What I want to tell you is, let's do this first. So x is our number, and then divide x to 2, and let's print the remainder and the quotient so that you can see how it looks like. So 13 divided by 2, let's run it. It's 6 as the quotient and 1 as the remainder. So see, like, we're very small program, did everything that you wanted. But if you want to go with the divide function, then you need to round it, then you need to multiply the round to 2, and then subtract it for you from your initial number. And that's gonna make a bigger program, like maybe this size of a program. So what I want to tell you is that whenever you want to program something in LabView, it will be really smart if you check and look at all the functions that LabView have and see if for a specific thing that you want to do already has a function built in LabView. This way you'll have a smaller program, it will be easier for you to debug your program, and in the future, for whoever who wants to work on your program, they can read your program easier. So just keep that in mind. It won't hurt if you do everything by yourself and program everything by yourself, but it's not smart if there's already a function that can do that. So I'm gonna delete this part and keep this part. So we are gonna divide our decimal number, which is our control, to 2. So decimal number and our control of 2, they're sending signals to a function, and that function is going to give us a value. So here, the way that we find a binary number is that we divide that number to 2, keep the remainder, and then divide the quotient again to 2 and keep the remainder. So something like that. So here, this node is my my quotient, and this node is the top node is the remainder. So you can always click Control C and Control V and copy it, or you can always come here and then add more. So we basically need 8 of them, because in this specific problem we want to find a binary number of a decimal number which is smaller than 256, and 256 is basically 2 to the power of 8, and that means that we need 8 slots to have this program run perfectly. So I'll keep adding until I have 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. That means I will divide the quotient value 7 more times. So the floor value is our quotient, and it's going to be our next x, and this is going to be divided this time again by 2. So here, I just want to keep showing you this. So our quotient value is going to be our next x that is going to be divided by 2, and we'll keep the remainder. So I'm not going to wire the remainder to anything yet, but I'm just going to continue building this part. and then divide it again by 2. The floor is going to be our next number, and then it's going to be divided by 2, and so on. So we needed the floor or the quotient to for our next dividing and our next dividing and so on. But what is important and what the user actually here wants to see is the binary number. So the remainder is what is needed. So that's why we have to create an indicator for a remainder, so that will show here the user what that for that specific slot out of those 8 slots, if that number is 0 or 1. So I'm going to name it from 1 to 8, and we're going to create an indicator out of all these functions that we had run so far. And these are indicators because these are what a user sees as the results. So these are the outputs, and because these are the outputs, a user actually see them. So I guess I had 2, 4, 6. I have left this one because it should have been 8. So I left one of them. I'm gonna rename them. Six, 7, and 8. Okay, so this is how it's been showing here, but this is not okay. It's really confusing for the user. So the responsibility of you as a programmer is to program something and print a proper result. This will print a proper result, but it's not in a proper order so that the user understands it. So you need to program a problem and have a proper results out of it, but you need to make it readable for a user too. So the next step for us is to rearrange these numbers so it's readable for the user. So based on this, so I'm going to go back again to here. The first remainder that we are going to read is going to be our corner right number. So that's why we'll have 1 in here and then start filling it till 8. So 2, okay, 3, 4, 5, 6, 7, and 8. And I'm going to select these all and I'm going to align them. Okay, so now for the number 13, let's see what is it in the binary format. Let's run it. So 13 in binary format is 00001101. So this so far is fine and it's producing the results that we want. So let's save it. I'm going to name it decimal to binary. So now say that we need some LED lights here that is going to be turned on whenever that specific slot is 1, and it's going to be turned off whenever that specific slot is 0. So for that, we need what? We need an LED light. Where we can find an LED light is on the front panel, because this is something that the user wants to see. So it's the visual for the user. So we right click on the front panel, go to Boolean, and then choose around LED. I'm going to choose this one. And I'm going to call this number 8, because 8 is underneath the 8. So I want them to be consistent. And I'm gonna keep having more of them by copying them. Or you can just add them from the front panel. You can either come here and then add them from the front panel, or you can copy them, whatever way that you feel more comfortable. It doesn't matter. This way for me it's faster, but as I said, whatever way that you feel more comfortable. This is tricky. Just keep in mind how long it's gonna taking me to prepare this model, this program. Just one by one, I have to one by one add all these booleans, add all these functions, and do this all one by one, and see how big the program gets and how not clean it looks. So we are gonna move them close to their spots for the next step, which is sending signals to them, which is important. So I am rearranging them. Notice that I'm rearranging them in the block diagram, but sorry. Oh my god. So I'm rearranging them in the block diagram, but they are not replaced in the front panel. So it doesn't matter where you put them in the block diagram. They are not gonna be moved in the front panel. Wherever I have put them in the front panel, they're gonna stay there. So they are not kind of like, they are connected in terms of their values, but not in terms of where they are actually put in the program. So we wanna see here whether our remainder for slot number 1 equals to 0 or if equals to 1. So you can, based on what I have actually taught you from before, you can have a case structure here, a case structure which is a true or false, and you can have a comparison here and say, is my number equal to a constant value of 1? Sorry. So if my number is equal to 1, and if it's equal to 1, it's true, and then turn on, sorry, just want to make it a little bit bigger so you can see. So here I'm going to say that is my remainder for slot number 1, is it equal to 1? If it's true, go to the true section and turn this on. On. If it's false, just, I don't know, like turn this off, something like that. So you can see if I run it, this is on. You can either program it like this, it's perfectly fine, but it's a lot of wirings and a lot of things. And based on what I told you, there might be some functions that can do this for us easier, because we only want to see if this number is equal to 1 or not. That's it. We don't want to do anything else. Actually, maybe, yeah, so forget about it. So this is like one way to do that. But let's delete this part. So I'll say remove case structure, and I'm going to remove all these things that I just told you about. Just keep it clean as it was before. So now, before me programming it, what I will do is that I'll come to different functions and I will look at them and see if I can find any function that is going to be useful for me and make my program cleaner, because someone in LabView already did that and make my life easier. So in the comparison palette, because you just want to compare whether this is equal to 0 or 1, you open the comparison palette and then you come and see, and here we have equal to 0, not equal to 0. So we can, this is useful. It's just this function only see if this is equal to 0 or not. So if it's equal to 0, if you use this function, it means that if it is equal to 0, true. So true means a light LED bulb. And a false means a turn off LED bulb. So we don't want that because we want the LED light to be on when it is equal to 1. So let's choose this one, not equal to 0. So if you choose not equal to 0, whenever it is not equal to 0, it will be turned on. It will be a true value. And yeah, we only have 1 and 0 here. And whenever it is not equal to 0, it means that it is 1. And that's what we want. So we will choose this function here. And what it says that give me the value of x, and you're giving the value of x to it. And I'll print whether x is not equal to 0 or what. So if x is equal to 0, the output is going to be false. But if the input or the x is another number which is not 0, like 1, the output is going to be true. So notice that the input, let me delete this. Notice that the input node is orange, so it needs a number, it needs a floating point number. And our number is our remainder here is our number 1. You can as I told you, you can pick any point on this wire because it doesn't matter. Anywhere in this wire has the same number, a floating point number. You can connect this anywhere. So it's not like a resistor in electrical engineering field that depending where you put, you might have a different voltage because your resistor is changing things. It's not like that. Anywhere on this wire, you'll have a value that are similar anywhere. So I can either connect it like this, or I can just come and connect it straight to the triangle here. So it doesn't really matter. But this has to read a signal, so it should get a signal, and here it will send a signal out, and that signal is either true or false. And because of that, because it's either true or false, you will see the color of the wire to be green, and the node is also green. So now let's try this one. It will get the value, it's either 0 or 1. It will compare it to see whether it's equal to 0 or not, and it will send a true or false value, and it will turn on the LED bulb. Let's try it this way again. So again, see, 1 is not equal to 0, so it is true, so the LED light will be on. I will turn on the light bulb here, and we can test that. So with the light bulb here, we can see the results, and you can see the true and false value here, so you can understand a little bit better. So see, it produced the true, and now it's producing all these values here. So I'll do it one more time. So 12 divided by 2, and the remainder is 1, and 1 is not equal to 0, so that's true, and it will turn on the light bulb. So we will do the same thing for all the remaining remainders. I actually gonna copy and paste. Sorry, I know it's just taking time for me to do that, but this basically I'm giving you time to do the same thing yourself too. I really suggest that you just don't watch the videos, but actually repeat what I'm doing here, because it's gonna be really helpful. I have connected it wrong. I should connect it to the 3, and then a 4 should go to a 4. See how hard it is if we want to program it this way? So in the next video, I'm going to show you another way to program this problem, which is easier, faster, and less there's less chance for you to make mistakes. Like here, there's a high chance that you make a mistake by wiring things to a not correct spot. So a 7 should go to a 7, an 8 should go to an 8. So basically it was really helpful to rename all these indicators from 1 to 8. So it will be easier to find the correct LED light bulb for it. So now all the remainder values from 1 to 8, they are being compared to 0. And if they are equal to 0, this function is going to produce a false value, and the LED light bulb will be off. But if they are equal to 1, the LED light will be on. So we know that 13 is 1, 0, 1, 1. So these two light bulbs should also be turned on if I run this program. And you can see they are on. So we have programmed it right. So for example, 255, they're all 1, which is correct. Okay, great. So I'm gonna save the program. Yeah, I want to show you this. So this program actually is finding a binary number for a decimal number, a decimal integer that is smaller than 256, and we are having 8 slots for it, and whenever there is a 1 it will be turned on, and whenever it's 0 it will be off. In the next video I'm going to show you how to program the same problem cleaner by using a for loop.